Hi guys, it's Matt Storm here with a video about rational equations. What are rational equations? A rational equation is an equation containing at least one rational expression. The equations we learned in the past, such as linear and quadratic equations, are called polynomial equations. Rational equations include polynomial equations and fractional equations. The roots of an equation. The solution of a single variable equation is also called the root of the equation. We aren't referring to the roots of a chemical equation, as shown on the right. There are three main steps in solving rational equations: eliminate, solve, and check. The first step is to eliminate denominators and convert the equation into a polynomial equation. Then, you solve the polynomial equation. When you get the possible answers, you have to check for extraneous roots. If there are any, eliminate them. What is an extraneous root? You might remember from one of my previous videos that I have slightly covered extraneous roots before. Except it's even more important in rational equations. In radical equations, it will be simply if the square root is less than 0. In rational equations, it occurs more often because you cannot let the fraction equal to 0 or else it's undefined. This is why I stress so much of checking for extraneous roots. When manipulating the original rational equation, the process may generate some roots that are not applicable to the original equation. These roots are defined as extraneous roots of rational equations. The method to solve for extraneous roots: simply plug roots into the denominator and check whether the denominator is equal to 0. If so, then the root is extraneous, and we need to eliminate it. If not, then the root is applicable to the original rational equation. The two conditions of extraneous roots are: number 1, the root is the solution of the polynomial equation. Number 2, the root makes the denominator equal to 0. So why should you check for roots of rational equations? When converting a rational equation to a polynomial equation, we expand the range of unknown variables. The denominator in the rational equation must not equal 0, but there is no such limit in polynomial equations, so we must check for roots in rational equations. Let's do an example. Solve the equation x squared plus 2x divided by x plus 2 in parentheses squared equals to 5. Solve this problem. So, once you see a fraction, you should directly eliminate the denominator. Of course, you will check for extraneous roots later. For this problem, after eliminating the denominator, we will get x squared times x plus 2 in parentheses squared plus 4x squared equals to 5 times x plus 2 in parentheses squared. After this, you arrange the like terms to get x to the power of 4 plus 4 times x to the power of 3 plus 3 times x to the power of 2 minus 20x minus 20 equals to 0. If you're stuck here, don't worry. You can factorize this expression by the rational root theorem. Squared times x squared plus 4x plus 3 in parentheses minus 20 times x plus 1 in parentheses equals to 0. We are simply factorizing the like term. You can factorize the first expression even more. X squared plus 4x plus 3 can be factorized by the cross method, which we learned in intermediate factorization. They will equal to x squared times x plus 1 times x plus 3 minus 20 times x plus 1. This will equal to 0. You then factorize out x plus 1, and after simplification, you get x plus 1 times x minus 2 times x squared plus 5x plus 10 equals to 0. From the first two parentheses, you get x equals to 1 or x equals to 2. If you wonder why I don't find the roots of the third expression in parentheses, this is obvious. Using the quadratic formula which we learned in a previous video also, you will find out immediately that a delta will equal and less to 0. So that is why we can not eliminate the roots of the third parentheses. You will find that x equals to -1 or x equals to 2 both work to the original equation. Thanks for watching.